Okay, so for the first part here of 2-2 notes, we start by just kind of reviewing acceleration a little bit again. So we first define the average acceleration, right? When we talked about average acceleration, and where that line above it just represents the average. It's my change in velocity over time. Well, keep in mind, change in velocity, right? There's two ways that we could do that. The two ways that we could change velocity would be either change the magnitude or the direction, right? So because velocity is a vector, we do have those two means of doing it. And then I throw in this important note down here. So it is, and it's worth thinking about, right? The average acceleration vector will point the same direction as the vector representing the change in velocity. And maybe it's tough to kind of visualize that. We'll see a few examples in just a second. But really what that's saying is if I've got a velocity going this way, so if this is my first velocity, and then my second velocity ends up going this way, well, the acceleration vector is going to point in the same direction as that change in velocity. So in other words, as that resultant between those velocities. So I know that the change in velocity would be this vector here. Now the acceleration, the one thing you do have to be careful about, the acceleration is not necessarily the same magnitude as the change in velocity, but it will point that same direction. Okay, so the acceleration would point this way, but not necessarily be as long. And the reason for that is I don't know the time, right? If I take my change in velocity, which if I think of this as a vector, and then I divide that by some scalar, well, if I divide it by a scalar that's bigger than 1, then the acceleration would obviously be smaller than the original vector. But if I took that change in vector and divided it by 0.5, that acceleration would actually be twice as long, right, as that original vector. So the only thing we know for sure is that the average acceleration vector will be the same direction as the change in velocity, but keep in mind we don't necessarily know that the magnitudes would be the same. But anyway, let's get a couple more examples of how we can visualize this. So to review that, let's actually go back to something we saw last year, which was uniform circular motion. So if we know it's a uniform circular motion, I know it's uniform because each of these velocity vectors is the same length. So that's telling me it's maintaining the same speed as I go around the circle. And obviously it's changing at the same rate. So we'll assume that this is over the same period of time. So I'm just going to choose these top two vectors to work with. I'm going to call this Vn, and then this one Vn plus 1. Right? So this is some vector, whatever order it comes in that sequence, and then this is the next vector over. Well, going back to what we talked about last year, I know if I have a uniform circular motion, which way should the acceleration always be pointing? Well, we talked about, right, the fact that if the velocity is changing direction but not magnitude, then the acceleration better be perpendicular to the velocity. So the acceleration would always have to be pointing towards the center of the circle if and only if it is uniform circular motion, meaning the velocity stays, or the speed stays the same, right? The magnitude of the velocity stays the same. So let's use this example to illustrate that. Well, if I take these two vectors, right? So if I take my second vector, my Vn plus 1, and then I subtract, I'm finding the change, so I subtract this first vector. Well, in order to subtract a vector, I'm going to reverse that direction, right? So I'm taking my first vector here, my Vn plus 1, and I'm subtracting the one right before it. And so to subtract, I'm going to start here, but then I'm going to work the exact opposite direction. And when I do that, because they're the same magnitude, right, I end up with a result that goes straight down, which in this case would be straight towards the center of that circular motion. Okay, so even if we didn't necessarily know that uniform circular motion should have an acceleration pointing towards the center, this example hopefully illustrates that because the change in velocity vector points towards the center of the circle, that's the same as the direction for the acceleration. Now again, keep in mind, the length of the acceleration could actually be shorter, it could be longer than the change in velocity, but I do know that that direction is pointing towards the center of the circle. So a little bit of background. I know probably spent more time on that than I needed to, but I do think there are some important points for us to consider here with vectors. And so let's see another example of this. So in this case, it's actually an example of non-uniform motion, right? And how do I know it's non-uniform motion? Well, if I look at the length, if I look at the magnitude of these two vectors, right, it's pretty clear to tell that those aren't equal. So if I want to find the acceleration, if I want to find the direction of the acceleration between the two vectors provided, obviously they don't give me any numbers to work with, but they do give me the directions here. And so to do that, again, I would start with my second vector, minus the first one. So I'm starting with this green one, I'm just going to leave this one here. But then from that endpoint, I'm going to reverse this direction because I'm taking Vn plus 1 and I'm subtracting the one before it, right? That's what we're doing for our change in velocity. So starting at this location, I'm going to try to go back relatively parallel to this first vector here. So it's going to go back something more or less like that, maybe, about the same direction. So then the resulting acceleration would be somewhere in this direction. Again, I don't actually know how long it is. Maybe the acceleration is only that strong. Maybe it's stronger. I don't necessarily know that. So I'm actually, maybe to illustrate that, I'm not going to have it connect all the way. Maybe I'll just leave it right there. But I do not know for sure that the acceleration would be in the same direction as the resultant between those two vectors. So again, this is if I'm subtracting the Vn vector. Right? So I do want you to be comfortable, regardless of whether you have magnitudes and numbers to work with or whether you just have these visual graphical examples here. I want you to be comfortable finding the direction of the acceleration based on the change in velocity. So a couple hopefully easy enough examples once you get a feel for it. But again, if that's the type of thing you want more practice with, just let me know so we can work on that a little bit more. This is another example that basically just has us illustrate this situation. So a ball rolls down a long hill through a valley and then back up the other side. Draw a complete motion diagram for this ball. And then it does ask us here, which it doesn't always, but in this case it wants us to show the velocity and the acceleration vectors in doing so. Okay, so I'm going to make it just kind of a gradual slope down, right? And then it'll be eventually a gradual slope back up. So I may move that here in just a second, but the hill itself is a valley of some kind here. So it goes something more or less like that, and then that's where I'll move this guy back over to connect. Okay, so I've got a gradual slope down. I meet the bottom of that valley, it goes through that valley, and then it goes back up the other side. So they want me to draw a motion diagram of the ball, including both the velocity and the acceleration vectors. Okay, so motion diagrams, right, we're going to try to show everything we can in terms of velocity, position, and acceleration. So if I release this ball from rest, I know its initial velocity would be 0. So I actually wouldn't need a velocity vector on it. But I would want to indicate the fact that its acceleration is going down the ramp. Right, so if the acceleration in actuality is pulling straight down, there is a component, and so the net acceleration for this object would be going down the ramp. Right, so there's its acceleration going down. Sometime later, so maybe the ball is now here, at some instant later, right, it's going to have the same acceleration going down the ramp. Right, and how do I know it's the same acceleration? Well, the angle of the ramp, the angle of the slope here hasn't changed. And so since gravity is constant and the angle is constant, I know that acceleration should be the same. So I know mine aren't perfect, but those two should be about the same length. Now at this point, however, it does have some velocity. Okay, so I'll just throw that velocity kind of right above the acceleration because it's now starting to move right down the ramp. The same amount of time later, so maybe another additional 1 second later, it's going to have covered more distance, right? So the separation here should be increasing a little bit more. Once again, the acceleration vector should be constant with those first two, but then the velocity vector at this point would be much greater, right? The velocity vector at that point would be much greater. So then as I approach the bottom of the ramp, so maybe my next position is down here, right? Well, in this case, what is my acceleration doing? Well, it's no longer just pointing down the slope, right? Because now my ball also has to turn as this ramp goes through that somewhat circular portion of the motion, right? So my acceleration at this point is actually going to start to pull kind of towards the center of that circular motion, right? Now I don't have enough numbers to know the specific length of that acceleration, but I do know that it's going to be pulling partially forward because it's still picking up speed as it rolls down, but also partially directed towards the center of that motion, right? The velocity, on the other hand, would always be tangent to the ball's motion here. So my velocity vector at this point is a little bit higher, so it's a little bit longer, but it's still forming a tangent line with that curve. So then again, maybe another equal space, another equal spacing interval, right? So an equal amount of time later, but not necessarily an equal amount of distance later, is what I was trying to say. But anyway, the acceleration at this point, right, would actually then still be directing towards the center of the circle. and therefore, because it's now starting to work against the velocity of the ball a little bit, the velocity would start to slow down as it goes back up the ramp. So this would technically be a little bit shorter than this one down here, right? Because as it starts to return back up the ramp, that velocity should be getting shorter and shorter. Now once the ball is actually fully going up the ramp, we know the velocity would be going this way, getting shorter, but keep in mind now the acceleration would be going straight down the ramp, right? So again, at this point sometime later, the velocity continues to diminish and the acceleration continues to stay the same, but going down the ramp. Okay, and then finally maybe it reaches the highest point up here, where once again it has no velocity, but its acceleration would still be going down the ramp, so presumably it would go right back down the hill and repeat this process all over again. So basically the point of this, more of the story, make sure you're comfortable with what the acceleration does as it goes through a curve. Make sure you're comfortable with thinking about it as the change in velocities, because really I could think about this acceleration as the change between this velocity and the next one over, which would be something kind of pointing back the other direction. And then obviously just throwing the accelerations into these motion diagrams. So hopefully you were able to muddle through this as I muddled through it here, and wasn't too bad, right? So then example 3 here is kind of just a quick conceptual check, right? So based on this diagram where I have my velocity going off to the left and the acceleration down and to the right, what will the actual particle do, right? What will the acceleration cause it to do? Speed up and curve upward, speed up and curve downward, slow down and curve upward, slow down and curve up and downward, move to the right and down, reverse the direction. Well, again, we know that the acceleration is a vector, and so I can break that into components. So the acceleration is pulling partially against the velocity, but partially downward, right? Well, the component of the acceleration that goes against the velocity is going to cause my velocity to slow down, because we know that anytime the velocity is going one way and the acceleration is the opposite, that object is going to slow down until eventually it reverses directions. But in the immediate time, it's just going to slow down. And then this component that's pulling downward will obviously cause the direction of my particle to curve downward, right? So this acceleration would cause the particle to slow down a little bit and curve down as well. So the velocity would continue to decrease as that object, that particle, curves down. Hopefully, my guess is you guys probably handled this one okay, but if you need to see it, there. So then this is where we get to kind of the fun stuff. This is really where we get to the heart of this second section here. And it looks way more complicated than it is. So if I ask you to find the average velocity from a graph, we know that we could do the following. Right? Normally if I ask you to find the average velocity, now keep in mind, if you actually look closely at the graph here, this is not what we're used to, because it's not a position versus time graph. Right? If I showed you a position versus time graph, and I asked you to find the average velocity between, say, this point and this point, well, the way that I would find the average velocity on a position versus time graph would be simply to find the slope between those two locations, because the slope would equal my change in x over my change in time, which is my velocity, right? Doing it on this graph is a little bit different, and we're going to look at why, right? So this one's not mapping position versus time, it's actually mapping the vertical displacement versus the horizontal displacement. So it's in a sense mapping my position versus position. This graph here is really actually showing what the object would do if I take it and I throw it through the air. So after 1 second, maybe the object is here, where it's over 1 meter, up 1 meter. After 2 seconds, maybe it's over here, where it's over 2 meters, up 1.5, or whatever, right? But this one's actually showing me the physical position of the object with respect to both the x and the y axis. So then, to find the average velocity, I would need to find my average change with respect to time. And keep in mind, I actually don't have any time on here, right? So all this graph is showing me is the direction of the average change in motion. I don't actually know how long the velocity is. So the part that we'd have to be careful about is we would know the direction, we'd know the direction of that change in position, but we actually wouldn't know the magnitude of the velocity unless they gave me time. The other thing that I want to go ahead and jump into here before this part of the notes ends, right? When I give you delta x over delta t, delta y over delta t, really what this is indicating is I'm going to be looking for my change in run over time and my change in height over time. So all this is saying is if I wanted to find my x component of the velocity, I know my x component of the velocity would be how far did I go horizontally and how long did it take. This here is just telling me my y component of the velocity. Okay, so we'll pick up fully with this and then into the instantaneous stuff as well for the next part of this video.